Hello and welcome to the next lesson in the lesson series of the binomial heap. Let's see what we have already talked about in the previous two lessons. We had talked about the binomial tree, binomial tree's example. We had seen what are the structural properties of binomial tree. We had seen an example how we can create a binomial tree. Then we had seen the definition of the binomial heap, an example of the binomial heap, and we have already seen the operations on binomial heap. We had talked about how binomial heaps are represented in the form of a linked list. And then we have seen the operation binomial heap creation, its time complexity. We had seen how minimum key can be found in the binomial heap with the help of an algorithm. We had seen the time complexity of this operation, and we had already seen an example how we can find out the minimum key in binomial heap. Today, we will talk about some more operations. We will talk about the union in binomial heap, and then we'll talk about the insertion in binomial heap. So let's see a simple procedure of how two binomial heaps can be united into one binomial heap. Let's talk about this procedure. Step 1. We'll merge H1 and H2. That means we'll link the roots of H1 and H2 in the non-decreasing order. This is the step 1. Step 2. Then after merging, it may be possible that the binomial heap property is violated. So we need to restore binomial heap property by linking binomial trees of the same degree together. Let's say if we have two binomial trees with degree 0, then we will link them together. Then we'll traverse the linked list, keep track of 3 pointers. What are these 3 pointers? Previous, PTR, and the next pointer. According to these, there may be 4 cases alive. 1. Degrees of the PTR and the next are not same, then we'll move ahead. We'll not do anything. Case 2, if degrees of next to next is also same, then again we'll move ahead, we'll not do anything. Case 3, now if key of PTR is smaller than or equal to the key of the next, then we'll make the next as a child of the PTR by linking it with PTR. If you remember, we had seen the property of binomial heap that in a binomial heap, we cannot have more than one trees with same degree. In that case, we need to link those trees following the min heap property. Case 4, if key PTR is greater than the next one, then make PTR as child of the next, because we need to maintain the min order heap property. Let's understand this with the help of an example. So here we have two heaps, heap 1 and heap 2, and we need to perform the union operation in these two. So step 1, if you remember the step 1, merge H1 and H2. That means we link the roots of H1 and H2 in non-decreasing order. So let's go and merge. So we'll merge these two. You can see we have merged both the heaps together in the non-decreasing order of their degree. So we have this as 0 degree, this with 0 degree, this with 1 degree, this with 1 degree, this with 2 degree, and this with 4 degree. So we have merged these two. Now we can see that the binomial heap property is violated here, because in this heap we have two trees with same degree, which is not possible. We cannot have more than one tree with same degree. So what we need to do is we need to link these two same degree trees together following the min heap property. That means the smaller key value will be in the root and the larger key value will become the left child of the root. So you can see here 12 and 18 are of same degree. So we need to link them, and key of 12 and key of 18. So we can see key of 12 is smaller. So this will remain in root and the other one will become the left child of this. So you can see here this is 12 and 18 become the left child of this. So this is how we have linked these two same degree binomial trees here. Now again, we can see we have 1, 2 and 3 binomial heaps with same degree. So what we need to do is we'll come to X. Now we'll check next of X. This is with the same degree. So we'll move ahead. So this is next and next of 8. This is 3. We'll move ahead. So now this is with higher degree. Then what we need to do is we need to link these two same degree trees. We need to link these two same degree trees. Again, following the min heap property, this is with key smaller and this is with key larger. So this tree will become the left child of this 3 key value node. So let's see in the next, you can see this is 3 and this is the left child now of the node with key value 3. Again, the binomial heap property is violated. As we can see, we have two trees here. This is tree 1 and this is tree 2 with same degree. Then again, we need to merge these two trees. Link these two trees following the min heap property. Now we'll see the key of the root nodes. This is 3 and this is 16. So we can say this is 15. So we can say that which one is minimum? 3 is minimum. So this will remain in the root and this tree, this subtree will become the left child of the 3. So now you can see this is 3 remain in the root and the next tree will become the left child of this root. So this is how we have merged two trees H1 and H2 and finally we have this union. So we can see here all the properties of the binomial heap are restored. We have the root nodes in non-decreasing orders and we have min heap property and all the trees are with different degrees here in the heap and all the other properties of the binomial heap are restored. So this is how we perform union of two binomial heaps. This is a simple algorithm that is we have already seen in the help of the procedure. You can take the snap of this algorithm and you can then write here in your copies. You can go back and you can pause this screen. You can take the snap and then you can move ahead. Now let's talk about the time complexity of the union operation. Basically, this union operation, H1 contains N1 nodes and let's say H2 contains N2 nodes. Then H1 contains at most log of N1 plus 1 roots and H2 contains at most log of N2 plus 1 roots. Now, if we'll add these two, log of N2 and log of N1 plus 2 will always be with the complexity of order of log of N. So now, the merge operation, also we have seen in the merge operation that it takes the order of log of n time. So the final complexity, the time complexity of this binomial heap union operation will be order of log of n. Now let's talk about the insertion operation. And as we can see that this insertion operation is basically the combination of two operations. One is the creation of binomial heap and then union of the two binomial heap, the newly created and the older one. So the simple procedure says step 1, create a new binomial heap H1 of one node of the value x, which is the new node to be inserted. Then step 2, this new binomial heap with one node is united with the older binomial heap. So let's talk about this procedure more. Insert binomial heap. We'll create a new binomial heap with the new value and that we'll set the parent of this will null, child of x with null, sibling with null and degree with null because this is a binomial heap with only one node. Then we'll set the head of this as x and we'll perform the union procedure on the two binomial heaps, the older one and the newly created binomial heap. The time complexity of the same will be order of log of n. So let's understand this insertion operation with an example. So here we'll do both these things. We'll create the binomial heap and then we'll merge the binomial heaps and finally in this way we are actually inserting a new element. So here an example, first of all we'll use all these key values and create the binomial tree and finally we'll also insert a new element with key 5. Basically we are inserting all the elements one after the other and we are creating the binomial heap. So let's start. We have to insert 7 as we do not have any tree. This 7 will be a new node and this will be a binomial heap with a single node. This is indicating the head of the binomial heap. Then we'll insert 2. So just to insert 2, we'll create a new binomial heap 2 Then we'll perform the union of these two, the older one 7 and the new one 2. And as we know, the property violation in a binomial heap, we cannot have more than one trees with same degree. So we need to restore the property. At the time of restoration, we need to link these two binomial heap min property taken to be considered. So we will compare the degrees of these two. So this is with smaller degree will remain in root, and this is with larger degree will become the left child of this 2. So now this is after inserting 2. You can see 2 is in root and 7 became the left child of the binomial this 2. The next operation, insert 4. So we can insert 4, we can create a new heap with 4, and then we need to unite that new heap 4 with the older heap 2 and 7. No property violation, we do not need to restore here. Next is we need to insert 17. At the time of insertion 17, so once we'll insert 17, we can see this will be the property violation because 17 with degree 0, 4 with degree 0. So we need to merge those 17 and 4 together. That will become 4 and 17 will become the left child of this 4. This will become the left child of this 4. Again property violation because this is degree with 1 and this will be degree with 1. Then we again need to perform the restoration of the property by linking these two trees. We'll compare the key values of this tree's root node and key value of this tree's root node. This is 4, this is 2. Obviously the smaller will become the root and the next will be the left child of the this 2. So now we have, after insertion 17, we have this as a tree, is this was at a binomial heap with now no property violation. Now let's insert 1. So next is 1. We'll insert 1. No property violation will be there. Again, we'll create a new heap with single node 1 and then we'll unite these two binomial heaps. No property violation. We can move ahead. Next is 11. Again, we'll create an 11. Then that 11 and 1 property violation. These two same degree tree needed to be merged together. One with low key value will be in the root and 11 will become the left child of this. So this is 1 and 11. Now no property violation. We can move ahead and insert 6. So now at the insertion of 6, first we'll create 6 as a new heap, then we'll unite these two. No property violation. We can move ahead and insert 8. So now once we'll insert 8, we can see 8 is a new binomial heap. Once we'll merge that h dash with this h, there will be a property violation because a new node 8 with single 0 degree and this is 6 with 0 degree. So we have two trees with the same degree. Then in that case we need to link. We will link 8 and 6 and again we'll compare the degrees. 6 with low degree, 8 with high degree. 6 will remain in root and that 8 will go down as the left child of 6. So now once we'll merge these two, again we'll have a property violation because at that time this 6 and 8 will be with degree 1 and this is another tree with degree 1 as well. Again we need to link and restore the property. We'll compare the key values of the root nodes. This is 1 key value, this is 6 key value. 1 is smaller, 6 is larger, so we need to link these two. 6 will become the left child of this 1. So now this will be the left child of this 1. So once we'll merge this, again we'll have the property violation because now this 1, 11, 6 and 8 with degree 2 and there is another tree 2, 4, 7 and 17 with degree 2. So now again we need to restore the binomial heap property and we need to link them and then we'll compare the degrees, the root nodes degrees. This is 2 and we'll compare the key values. So this is 2 and this is 1. 1 is smaller, so this tree will become the left child of this tree. So here we can see after the insertion of that we have 1, 6, 8, 11, 2, 4, 5. This is the left child of the 1 and now we'll insert 15. This is a single node. On insertion of the 15 there will be no property violation. Then we can insert 10. At the insertion of 10 there will be a property violation because the new node 10 will be a new heap with single node. the new heap with 0 degree, and this is again a tree with 0 degree. So property violation, we need to compare the key values. 10 and 15 will be compared. 10 will be smaller, so 15 will become the left child. So 10 is a smaller, 15 become the left child of the new tree. Now we can go ahead and insert 20. So once we'll insert 20, no property violation. So now the last element, insert a new element with key 5. As soon as we'll insert 5, the property violation will occur because the 5 heap with 5 with 0 degree, 20 with 0 degree. So we need to link them, seeing the key values. 5 is smaller, 20 is larger. So 5 will remain in the root and 20 will become the left child of the 5. So 5 and 20 will be a tree with degree 1, and here 10 and 15 with degree 1. Again, property violation. We need to check the key values of the root nodes 5 and 10. 5 is smaller and 10 is larger. So this tree will become the left child of this 5 root node. So this is become the left child of the 5 root node. So this is how we can insert all the key values, and finally we have this binomial heap with no binomial heap property violation. That's all for the today's lesson. We had seen how we can unite two binomial heap, and we had seen how we can insert key values into the binomial heap. In the next lesson, we will be talking about remaining three operations, that is the extract minimum key, decrease key, and delete key operations into the binomial heap. So uh, that's it for the today's lesson. If you have any queries, any confusions, feel free to use the comment box and ask your queries. Thank you so much.